Welcome to Creative World. In this video, we will solve Chapter 3 exercise problem number 3.5. While solving this problem, we will be using Kirchoff's current law. According to this law, a cumulative current on a node inside an electrical network is always equal to 0. Sum of all entering currents on a node is always equal to sum of all leaving currents from that node. We also will be using Ohm's law. According to this law, voltage across any resistance R is the product of current through it and the value of resistance itself. Now move towards the problem. Exercise problem number 3.5. Use nodal analysis to find the value of voltage V1 in given below figure. This is the circuit diagram of given problem. Inside this network, we have to find the value of voltage across this 3 kilo ohm resistance labeled as V1. So without wasting time, let's proceed towards the solution of the network. We know that in order to apply nodal analysis on any network, we have to follow some steps. The first step includes finding out the number of nodes in that network. In this network, there are three number of nodes. One of them will be considered as reference or ground node. Other two nodes will be used to apply nodal analysis. In second step, we have to label all unknown node voltages. In this case, we are considering this node voltage as V1 and this node voltage as V2. In next step, we have to assume all unknown branch currents along with their directions. Now we will apply Kirchoff's current law on this first node to find out its node voltage equation. On this node, only one current is entering while two currents are leaving. So KCL equation for this particular node will be entering current is taken with positive sign while leaving currents are taken with negative sign. I3 minus I1 minus I2 equal to 0. In next step, we have to replace these currents with their respective equations. Current I3 is flowing between these two nodes and the direction of this current is from right to left. In order to find the equation of I3, we should have the value of voltage across this resistance. That voltage divided by the value of resistance will be equal to I3. In this case, this resistance exists between two non-reference nodes. So voltage across this resistance will be equal to the difference of these two node voltages. Now we will see the direction of current I3. I3 is flowing from node voltage V2 to V1, which means node voltage V2 is considered higher than V1. So the difference of these two node voltage across this 2 kilo ohm resistance will be taken as V2 minus V1 and current I3 equation will be V2 minus V1 divided by 2 kilo ohm. Similarly, current I1 will be equal to voltage across 3 kilo ohm resistance divided by the value of resistance. In this case, V1 is appearing across 3 kilo ohm resistance. So, current I1 equation will be V1 divided by 3 kilo ohm. Value of current I2 is already given in the form of constant current source. So, I2 will be taken as 6 milliampere. Now, in order to further solve this equation, we will multiply this equation on both sides with 6 kilo ohm to omit denominator values. Product of 6 kilo ohm and 2 kilo ohm in denominator will cancel out with each other. Only 3 will left. And that 3 will be multiplied with these variables. The equation will become 3V2 minus 3V1. Here product of 6 kilo ohm will cancel out with 3 kilo ohm in denominator. Only 2 will left and that 2 will be multiplied with V1. It will become 2V1. Product of 6 milliampere and 6 kilo ohm will result 36 volt. Now in order to further solve this equation, place this constant on the other hand side of equal and add values having same variables together. Equation will become minus 5V1 plus 3V2 equal to 36. We cannot further solve this equation, so leave it for now and label it as equation A. It is the first node voltage equation of this network. Move towards the second node. On this node, all currents are leaving. So KCL equation for this node will be minus I3, minus I4, minus I5 and minus I6. Because all currents are leaving, so all currents are taken with negative signs. In next step, we have to replace all these currents with their respective equations. The equation of current I3 as we have calculated in previous step is equal to V2 minus V1 divided by 2 kilo ohm. I4 is equal to 4 milliampere because of the constant current value, while I5 is equal to voltage across this resistance divided by the value of resistance V2 divided by 2 kilo ohm. Similar case will be with this I6 because V2 is appearing across this 2 kilo ohm resistance. So current I6 will be equal to V2 divided by 2 kilo ohm. Now in order to omit all denominator values, we will multiply this equation on both sides with 2 kilo ohm. The equation will become minus V2 plus V1 minus 8 minus V2 minus V2 equal to 0. All these denominator values are cancelled out with the product of 2 kilo ohm. Here the product of 4 milliampere and 2 kilo ohm will result 8 volt. Now place this constant value on the other hand side of equal and add values having same variables together. The equation will become V1 minus 3V2 equal to 8. We cannot further solve this equation, so leave it for now and label it as equation B. It is the second node voltage equation of this network. Now in order to find out the value of V1, we will add these two equations together. Equation A is equal to minus 5V1 plus 3V2 equal to 36, while equation B is equal to V1 minus 3V2 equal to 8. Here minus 3V2 and plus 3V2 will cancel out with each other. Sum of minus 5V1 and V1 will result minus 4V1. And on the other hand side of equal, sum of 36 and 8 will result 44. Now in order to find the value of V1, divide on both sides with minus 4. The value of voltage V1 will become minus 11 volt. Here minus sign with the value of V1 is indicating that the polarity of voltage V1 taken in this network is wrong. The actual polarity of V1 is opposite to the given polarity, which means the direction of current I1 is towards this node rather than leaving from this node. So this was exercise problem number 3.5. Thank you. See you again in next video.